Okay, so this page right here, we're going to fill out as we go through all of these different objectives in Unit 4. Unit 4 is a study of polynomials, and these are all the critical terms and ideas. It would be a great reference sheet when you're doing your quizzes, and if I give you a test, it would be a great thing to use and have out. Okay, so we're going to just be defining these two terms today because they are useful for what we're doing today. So we're going to start with the term polynomial. Polynomial is a continuous function. Okay, the difference between a continuous function and a non-continuous function is continuous functions you can draw across the graph, like this is a continuous function line right there, versus non-continuous, where maybe you do something like that and then you pick up your pencil and you do something like that. Okay, so polynomials are all continuous functions. All right, with no breaks, so you don't have to pick up your pencil in order to draw them in a single variable, meaning they're only in x or only in a or only in terms of y or whatever. Okay, containing one term to many terms raised to positive integer powers. Graphs will be curves unless it's a constant polynomial, constant function, or a linear function. Of course, constants are just flat lines and linears have positive and negative slopes. Okay, so that would be x to the, 0x to the first power is a constant, and a linear function would be like f of x equals x plus 2. That's a linear function. Constant would be f of x equals 4. And then you could just write plus 0x. So it's written in terms of x, it just has 0 x's in it. So those are both your constant and linear ideas. But let's do a depiction over here. So if we have f of x is equal to x squared minus x plus 1, this is a quadratic polynomial. And you can see that it's a polynomial because it's written in terms of x. And all of our x's are written to positive integer powers. If you want to remember positive, positive integers are 1, 2, 3, 4, ... Those are integers. Okay. Another option here could be the p of x is equal to x to the 5th plus 2x plus 5. There's another polynomial. Those are both trinomials that I've written there. They have 3 terms to them. You could also have a monomial like this. The g of x is equal to x cubed. That's another polynomial. As long as all of the variables are the same and the exponents on those variables are positive integers, it's a polynomial. Okay, not a poly would be something like this. The f of x equals 1 over x. That's not a polynomial because that's a rational function. The x is in the denominator. I could actually write 1 over x as an exponent, x to the negative 1. So that could also say f of x equals x to the negative 1. That's not a polynomial because the exponent on the x's have to be positive integers, not negative. Another one that you might see that you might wonder if it's a polynomial would be the square root of x. Square root of x is not a continuous function. It starts at 0 and goes to infinity, but it doesn't go to negative infinity, whereas all of these functions do go from positive to negative infinity. If I were to write this with an exponent instead of a square root, that would be x to the 1/2. So g of x equals the square root of x, or g of x equals x to the 1/2. These are both, these are not polynomials because 1/2 is also not a positive integer exponent or power, so not a poly. So that's how you know the difference between a polynomial and a non-polynomial function. Okay, let's move to intermediate value theorem. It says this: if f is a polynomial function, and the f of a, remember that's a y, right? And the f of b for different outputs are not equal, for a is less than b, then the function f takes on every value between the f of a and f of b in the interval between the closed interval between a and b. So what does that look like? So let's come over here and kind of give you a little depiction that will help you to understand what's happening here. So here we have our x-axis and here we have our y-axis. And a has to be less than b. according to this definition here, A has to be less than B. And the f of A cannot be the same as the f of B. So let's put the f of A down here. So that would be that point right there. And let's put the f of B up here. Okay? And so that would be that point right there. Now, since this is a polynomial function, I have to actually connect them with a curve of some sort. So I'm going to go ahead and do that. So maybe it goes something like that. Maybe it goes something like that. So basically what the intermediate value theorem says is that between A and B, I'm going to pick up all of the values along this line right here. I'm going to pick up all these outputs, all of these y's between here. So could you say, by looking at that there's a 0 between A and B? Because 0 is definitely in between this f of A, which is a negative A, or a negative value, and this f of B, which is a positive value. So all of the values in between the f of A and the f of B are going to be taken on by the function between point A and point B. All right, another idea here would, maybe a different idea here would be that, let's do another picture here. So here's A and here's B. So A is less than B. You with me? And let's say that we have the f of A up here and the f of B is down here. And so here's our f of A and here's our f of B. And maybe our graph does something like that. Maybe it does something like that. So the intermediate value theorem says that between A and B, because A is less than B, that between A and B, I really want a different color here, that the graph is going to pick up all of the y values in between the f of A and f of B. So in this case, there will also be a 0, or your f of x will equal 0 in between the f of A and the f of B, because the f of A was a positive value and the f of B is a negative value. And so per the intermediate value theorem, the function has to take on a 0 to go from the positive side of y to the negative side of y. It has to take on the 0 at some point. All right, and usually that's what we're using the intermediate value for, is to find out if there's a 0 between two inputs or two x values. So all right, so this is objective 4.1a. The topic today, the main topic today, is intermediate value theorem. It's going to be the new topic for today. I'm also going to do a little bit of a review of how to graph a cubic function, but that's just more of a review. So our two essential questions: how do I graph a cubic function? And number 2, what conditions must exist to apply the intermediate value theorem? So I just abbreviate it to IVT. Okay, so we're going to talk about two terms here: polynomial, which, well, we just defined in our critical terms page. So we're going to keep it simple. It's a continuous function, right? Continuous. In one variable. Containing terms raised to positive integer powers. Okay, all right, so that's important. The intermediate value theorem, we're going to set the conditions here, because these are the things that have to exist. So condition 1, if f, it's not if. F must be continuous. The function must be continuous. Okay, if it has a break in it, we can't use the intermediate value theorem. 2, the f of A, the outputs cannot be equal. The f of A cannot equal the f of B. And 3, A has to be less than B. Okay, so if these conditions exist, then we can conclude by the intermediate value theorem the function f will pick up all values between, right, because it's intermediate, the f of a and f of b. All right, over the interval, oh, let me mention that, over the interval between a and b. So over that domain of points, it's going to pick up all the y's in between the output of f of a and the output f of b. All right, so those are the two things we're talking about. So here's example one. We're going to be talking about our first essential question, how do I graph a cubic function? So here what we're going to do is actually fill out this table of values for negative x cubed. Okay, this is a degree of 3 polynomial, because the biggest exponent we have on our term is 3. So that means that the function could have up to 2 turning points. It could change directions up to 2 times, depending on how complicated this function is. And this is just the parent function of x cubed. All right. It's an odd function because it's a degree of 3, and our a term is greater than 0. So it's going to open up. But let's go ahead and just fill this out. If we do 2 cubed, right? If our x is negative 2 and we cube it, right? Negative 2 cubed, that's negative 8. Negative 1.5 cubed, I'm just going to give you these values, is negative 3.375. Negative 1 cubed is negative 1. Negative half cubed is negative 0.125. 0 cubed is 0. Half cubed is 0.125. 1 cubed is 1. 1.5 cubed is 3.375. And 2 cubed is 8. And so we could actually just go ahead and graph those. And I am going to use this table. I'm going to change my scale here. So that's going to be 1 and 2. And so I just so that, and I'm negative 1 and 1, negative 2 and negative 3. Sorry, let me be a little more careful there. All right, so what I want to mention here is you can see that I'm changing my x scale so that every other tick mark is a unit, but I'm not going to change my y scale. So this is going to skew my graph a little bit, but what I want you to see is the turning points. That's what's really critical here. Also, so I can get in the 1.5 and the negative 1.5, and I can graph all those points. So at negative 2, we're at negative 8. So that would be here. At negative 1.5, we're down 3.375. So probably about right there. At negative 1, we're at negative 1. And then at half, we're down at just right here, barely below at negative 0.12500. At half, we're barely up at 0.125. At 1, we're up at 1. And then at 1.5, we're up at 3.375, so about right there. And then at 2, we're way up here at 8. And so you can see a pretty good curve going on between the zeros between negative 1 and 1. You can see how the curve kind of starts to flatten out as it hits the origin. And then as you get past 1, it starts to get a really deep curve again. But this is your f of x, so there it is. And that's the parent function of your cubic function. So what we're going to do now is just sketch some graphs of a cubic function that only has vertical transformations. It doesn't have any horizontal transformations because the x isn't in any parentheses here. So we're sketching graphs for the f of x equals a x cubed plus c. Sketch the graph of the function for the indicated value of a or c. Now remember that a is your term that stretches and compresses the function. And then b, sometimes it's a b, but in our textbook today, well, you're not used the textbook. I don't know what I'm talking about. I should have just changed it to b for you. Let's change it to b. Let's just do that. We'll just change it to b. It's not a big deal. And so we'll make this a b here, and we'll make this a b here. There, now it's a b. And we'll make this a b. So now it's a's and b's. And you can see that we have the vertical actions there and the transformation form. There's nothing in the x in parentheses with the x. So there's no horizontal actions happening here. So here we're going to take the function f of x is equal to 3x cubed, and b is -1. So we're going to replace that with a -1. So this is taking the function, the parent function, y equals x cubed, and we're stretching it vertically by a factor of 3. So that means we're doing all our y coordinates times 3, and then we're shifting it vertically. We're going to go down 1. So that means we're doing 3y minus 1. Okay, so what you could do here is you could basically just graph the a couple of points here. So if these are, that's our -1, and that's our 1 and 0 and 2 and -2, and we're going to go 1, 2, 3, 4, 1, 2, 3, 4, 5, and then I think I'll put -5 in there. 1, 2, 3, 4, 5, just so we can see what's happening there. So our parent function, if you recall, we had a point at -1, 1, a point at 0, 0, a point at 1, 1, and then we had a point at 2. Let's clean that up. That should be 1 here. At 2, 8. So there was a point up here at 2, 8, and a point down here at -2. 1, 2, 3, 4, 5, 6, 7. It was way down here at -8. Okay, and then you had some other points, but we're just going to move those points. And I'm not going to draw the curve. I'm just going to move the y's. Remember, we're not affecting it horizontally, so we're just going to move the y's. So let's start with, I'm going to do this in red. Let's stretch by a factor of 3. So we're going to take this y right here, y equals 0, and we're going to multiply it by 3. That's 0. And then we're going to subtract 1. So that's down 1. So that's our new point on the, that's our y-intercept, in fact, is -1. Let's take this point here, right here, where y equals 1. So 1 times 3 is 3, and then down 1 would be 2. So that point's going to move to there. Let's take this one here. At y equals -1 times 3, that's -3, and then down 1 would be -4. And so here's where our graph would be. And it would do something like that. And there really isn't a way for me to graph these other points at 2, 8. If I were to multiply 2 times 8, that's 16. And 16 down 1 would be 15, and that's way up here somewhere on the graph. So I can't really graph that. And so there you have that. You're just using some vertical actions here to take this parent function that we graphed. Just the critical points, or the nice points at -1, -1, 0, 0, 1, 1. And stretch them or compress them or do whatever you've got to do and do your shifts. Okay, so here we have this one where we have the f of x is ax cubed minus 2, and a is -2. So we're doing the f of x equals -2x cubed minus 2. So that means we're doing a vertical, we have a vertical right here, a vertical flip. We have a reflection and stretch. So we're going to do y times -2, and then we have a vertical shift down 2. So basically we're going to be subtracting 2. So we're going to do -2 times our y and then subtract 2. Because that's what we're doing. That gives us the reflection, the stretch, and then the shift down. So if we take our original function here, here, and here, and here, and that would be -1, and this would be 1, and that would be 0. And this is 5. 1, 2, 3, 4, -5. Okay, so there's our original points on our parent function, and let's just take our y values. So I'll grab my blue pen. We're going to take our y values, multiply them times -2 to get the reflection and the stretch, and then shift that point down 2. So if we're taking this as y equals -1 times -2, -1 times -2 is 2, and then shift down 2, that would take us from 2 down to 0. this point here, 0, 0. Y equals 0 here times negative 2. That's 0. And then down 2 would be down here at negative 2. Then we'll take this point here where y equals 1. 1 times negative 2 is negative 2. And then down 2, negative 2 down 2 would be down 4. And so this one would be stretched and flipped. And you can see that that's happening. So you can see the vertical flip there. So now this is a decreasing function instead of these other two functions, which were increasing functions. And you're just using your vertical transformations of the parent function, which we learned last week. Okay, so now we're moving on to the intermediate value theorem. And what we're going to be doing is using it to show that a function has a 0 between two input values. Or if it doesn't have a 0 between two input values, we'll say that the intermediate value theorem doesn't help us to show if there's a 0 or not. So number 2 says, use the intermediate value theorem, IVT, to show that the function has a 0 between a and b. So recall that in order to do that, we have to have the function has to be continuous. If it's a polynomial function, then it is. That the output, the f of a, cannot be the same as the f of b, and a has to be less than b. Or b can be less than a. That could happen too. It just depends on how we label it. But in this case, the first input's less than the output. Well, the two outputs, one has to be greater than the other, basically. So that's what we're going to do. So basically what we're looking for is if there's a 0 between a and b, meaning that the graph does something like this, like if this is a and a gives us, or this is a and the f of a gives us an output down here, and this is b, and the f of b gives us a value that's up here. If it's a function, then it's going to curve through the 2 points and pick up all of the values between the f of a and f of b. So there has to be a 0 between them, that per the intermediate value theorem. So we're looking for that kind of situation. So let's go with this first problem here that says we have this polynomial function, the x to the 5th minus 2x to the 4th minus 6x cubed minus plus 2x minus 3, and we're going to find the outputs between a and b. So you can see that a is less than b. Okay, so a is less than b, so that's good. That's the first thing. And so let's find the f of 1, and we could plug that in. So that would be 1 to the 5th plus 2 times 1 to the 4th minus 6 times 1 cubed plus 2 times 1 minus 3. And we could simplify that really quickly. You can also plug it into your calculator if you want to. That would be fine. But when you raise 1 to a power, it's always 1. 1 times 1 times 1 times 1, it's 1. Plus 2 times 1 minus 6 times 1 plus 2 times 1, which is 2 minus 3. So we know that's 2 and that's 6. So if we were to add all of that together, 1 plus 2 is 3, minus 6 is negative 3, plus 2 is negative 1, minus 3 is negative 4. So the f of 1 is negative 4, and negative 4 is less than 0. So if I were to actually go and graph that, if I were to make just a visual representation of that, then the f of 1, this is our a, would be here at negative 4, and that would be our output. Okay, so then let's go to the f of b. So the f of 2, we're going to use that input. So that would be 2 to the 5th plus 2 times 1 to the 4th minus 6 times, 2 to the 4th, 6 times 2 squared plus 2 times 2 minus 3. So we're plugging in 2's now. 2 to the 5th is 32. This is 2 to the 1st times 2 to the 4th, which is also 2 to the 5th. So that'd be plus 32. This is a cubed. So that would be negative 6. That's 8. So negative 6 times 8 is negative 48 plus 4 minus 3. And then we put all of that together, and I'm going to go ahead and do that right now. It's just 17. And 17 is greater than 0. So the f of 2 So I'm going to go ahead and graph that. I'm going to put 2 over here. Is way up here somewhere at 17. Okay, and so the question here is to show that the function has a 0 between a and b. Well, because this is a polynomial function, here, this is a polynomial function, and it's definitely a curve because it's not linear. The graph has to, at some point, it has to have a 0 somewhere, because the values are between those 2 points. You're going to pick up all of these y values, all of them. So there has to be a 0 between them somewhere. There might be more than 1 0 depending on the graph, but there's at least 1 0. And you could graph it on Desmos to see it as well. So how do we write the solution? There's 2 ways. Formally, if I was writing this for a calc class, I would say, since the function is continuous, that's critical, that's piece 1, and the f of -1 is, the f of 1 is 4, and -4, let me clean this up, try it again, and the f of 1 is -4, and the f of 2 is positive 17, then there must exist a value for some point x equals some point c, we'll just call it c, such that the f of c equals 0 in the interval between 1 and 2 by the IVT, the intermediate value theorem. So formally, that's how you would write that solution. You would have to write all of that. But for pre-calc, here's what I'd like to see. 1, f is continuous. Check. 2, the f of 1 is -4, which is less than 0. And the f of 2 is 17, which is greater than 0. Therefore, and that's the 3 little dots right there, say therefore, by the intermediate value theorem, there is a 0. I think I'm going to say at least 1 0. In the interval 1 to 2. So that's, I think, a little bit less convoluted and makes a little bit more sense. And I really do like to do things like after I get these values, I actually do plot them so that I can visually see, since it's a continuous curve, that there has to be a 0 between them. And the 0 is your output. It means when y equals 0. Okay? So actually I'm going to put a point right here and call it point C right there. So that's going to be point C, whatever it is, for x equals c. All right, let's do one more. So here we have another polynomial function, x to the 4th, 2x cubed minus 13x squared minus 14x plus 24. And I've already used the calculator, so we're going to go through this process again. So we're going to do the f of, let me color code here. So we're going to do the f of 4.1 for a. A is less than b. Look at that. So the f of negative 4.1 means we're plugging in a negative 4.1 to the 4th plus 2 times negative 4.1 cubed minus 13 times negative 4.1 squared minus 14 times negative 4.1 plus 24. And I'm plugging all of that into my calculator for you. You should be really careful when you plug those in. So since this is a negative value and I'm plugging it in for x and I'm raising it to a power, I'm very careful to put parentheses around it. Very careful. So here's my output. It is 7.60 0, 4, 1, which is greater than 0. And remember, we're trying to prove zeros. So if the f of negative 3.9 is negative, then there must be a 0. So let's see this, negative 3.9. So we're going to plug in negative 3.9 to the fourth plus 2 times negative 3.9 cubed minus 13 times negative 3.9 squared. 14 times negative 3.9 plus 24. And so I plug that into my calculator for you as well. And we get the solution negative 6.424, which is less than 0. So negative 3.9 produced a negative. Negative 4.1 produced a positive. And so if I were to graph those on a coordinate plane here, so I'll just put negative 3.9 here and negative 4.1 here. It is definitely not drawn to scale, but the negative 3.9 produced negative 6.24. So this would be negative 6.24. 424, so negative 6.424. So that would be that value there. And negative 4.1 produced 7 point something, 7.6. That's good enough for us to get the idea. So since this is a polynomial function, then when we, somewhere between those two on the curve here would be point C, there would be a 0 between them. They have to, because this is a positive value, and then this is a negative value, and it's a continuous function, so it has to hit 0 so it can change sides of the x-axis. And so we would just say 1, f is continuous. 2, the f of negative 4.1 is equal to 7.6041, which is greater than 0. And the f of negative 3.9 is equal to negative 6.424, which is less than 0. Therefore, by IVT, by the intermediate value theorem, there is at least 1 0. 1 0. In the interval. Well, and we don't have to write the interval. We can just say in this interval between negative 4.1 and negative 3.9. And I'm actually going to show you both of these on Desmos so that you can see that these are actually occurring. And this is a way that you can check your work as well. So let me see if I can get my iPad to cooperate here. Okay, so our first one was, so I'm going to look at example 2a. So it was the f of x. If you don't mind, I'm just going to type in y because I don't want to type in f of x. X to the fifth plus 2x to the fourth plus minus, let's go back, minus 6x cubed plus 2x minus 3. So that's a pretty funky graph right there. Let me double check it. X to the fifth plus 2x to the fourth minus 6x cubed plus 2x minus 3. And our input and our outputs were between 1 and 2. So I'm going to change this so we can kind of zoom in here. There's 1. So 1 is giving us this output down here. You can see when x equals 1, y equals this value down here, negative 4. And then at x equals 2, look at what happens. I really have to zoom out here. When x equals 2, I'm way up here at 17. So you can see between 1 and 2, you can see the 0. It's right there at 1.634. So between 1 and 2, because 1 produced a negative and 2 produced a positive, and this is a polynomial curve, there had to be a 0 between the 1 and 2. In the second one, we had the f of x, but again, I'm going to type it in. It was x to the fourth. That's a funky graph, plus 2x cubed. Minus 13x squared. minus, was it a 13? 14x plus 24. All right, so we have to be way over here between 4.1 and 3.9. And so you can see to the left of negative, so I think there's a 0 actually right there. There's a 0 at x equals 4, which is right between 4.1 and 3.9. So if I really were to stretch it out, it's just really difficult to see. Let me change my x-axis to go from negative 50 to positive 50, and let's see if we can see it a little better. Okay, so there we go. So you can see that a little better. So you can see that there's a 0 between negative, on the interval between negative 4.1 and negative 3.9, because negative 4.1 produced a positive output and negative 3.9 produced a negative output. And you can see that curve is continuous. So by IVT, there you go. And that's it. So you're going to do some work like that today. Have a great day.